Okay, now let's start the class today. In today's class, we're going to study the fluid dynamic. So in previous classes, we mainly focus on statistic fluid, which means the fluid, they are stable. But now let's see when the fluid is flowing, what can we do? What problems can we solve by using some simple equations? This is fluid dynamic. So first, let's take a look at a fluid in a tube. And this tube is not a uniform tube. It's wider at some part and narrower at some other parts. So if we take a look at this tube, we'll see it's narrower at the beginning, it's wider at the beginning and narrower at the end. Now, let's take a look at fluid elements inside the tube. So here, at the beginning, if we take a look at a fluid element here, we can see there is a velocity for this fluid element. It could be V1. And here, if we take another fluid element, the velocity could be different. And here, the velocity is, of course, higher because the cross area of this tube at this section is smaller, then the velocity should be higher. Then, if we think about it, the fluid element, it flows from the beginning to the end of the tube. Actually, its velocity is changing from a low velocity to a higher velocity. When the velocity is changing, there must be acceleration. So here, this is acceleration A, and we know if the velocity is getting higher and higher, then the acceleration should be in the same direction with the velocity. Now, if we think about the reason of the acceleration, we know by Newton's second law, the acceleration equals to the force over mass. Then there must be some force or net force on the fluid element, especially at this region, so that it can change the velocity from low to high. So that's the origin of the acceleration or the velocity change. Okay, so a fluid element changes velocity as it moves from the wider part of a tube to the narrower part. This acceleration of the fluid element must be caused by a force, because only net force can result in acceleration. And this fluid element is pushed from both ends by the surrounding fluid, which is pressure forces. If we take a look at an individual fluid element, let's say one fluid element at this position, if we take a look at it, we'll see, first of all, it's a cylinder part or cylinder fluid element. So it has pressure on both sides. The pressure on the low speed side is pushing it forward, and the pressure on the right side, it's pushing it back. And we know the acceleration is going to the right direction so that it can getting faster. So the net force should go to the right. And then to accelerate the element, the pressure must be higher in the wider part of the tube, and the pressure gradient is the region where there's a change in pressure from one point in the fluid to another. So by taking a look at this figure, we know there must be a pressure gradient. An ideal fluid accelerates whenever there is a pressure gradient. Okay, and then the pressure is higher at a point along the streamline where the fluid is moving slower and lower where the fluid is moving faster. So for example, in this tube, we know at this side, at the left side, it's wider, and here it's narrower. So the speed at the narrower part is faster. And then we know, based on this analysis, we know at the low speed side, which is wider side of the tube, the pressure should be lower, or the force should be lower, and on the other side, the force should be higher. Then it results in the pressure difference. The pressure at the wider part in the fluid should be higher, and on the narrower part, it should be lower. Here, if we measure the pressure by using a venturi tube, which is open tube, a small open tube on the main tube, you will see the level of the fluid. The higher level of fluid, of course, means higher pressure. Then if you do an experiment in this way, you let the fluid go through the tube, we will see the height at wider and narrow part of the tube are different. First, at the wider part, the height of the small tube of the fluid in the small tube is higher than the narrower part. That means the pressure in this part, in the wider part, is higher. So this property of fluid was discovered by Daniel Bernoulli, and then it's called the Bernoulli effect. So eventually, Bernoulli effect states that the pressure at the wider part of the fluid is higher, and at the narrower part of the fluid is lower during the fluid flow. And this Bernoulli effect can be used or can be noticed in many daily life events. For example, as air moves over a hill, the streamline is getting denser so that the air speeds up. That's why when you're standing on the top of a hill, the wind is getting stronger. This is the reason. So if we look at the air lines or air streamlines, or the above the hill, you will see at a very high level, the streamlines, they're parallel. But when it's getting closer to the ground and the hill, you will see the streamlines bended, and on the top of the hill, the streamlines are much denser. And denser streamline means a faster movement of the air. And then a faster movement or a faster flow of the air result in the pressure, and it's a low pressure than normal. So if you stand on such a zone, then the pressure at this zone is lower. And this lower pressure can be used in the flight design. So in many airplanes, we use this effect, the Bernoulli effect, to lift the airplane. Lift is upward force on the wing of an airplane that makes flight possible. So this is cross-section area of a flight or airplane. So the wing of the airplane is in this way, if we cut it in the cross-section area, we'll see it in this way. So it's designed into a special shape so that when air go through or go passing the wings, the streamlines above the wing is denser, and streamlines below the wing is less dense. So because it's denser above, then the air flows faster above the wing, and then it's resulting in a low pressure. And below the wing, it's resulting in a high pressure. So high pressure and low pressure, there's a pressure difference, which results in a force difference. Then there's net force of lifting the wings up. Then that's the main force for the lifting force, which makes the airplane fly or lift the airplane. Okay, so the wing is designed such that above the wings, airspeed increases and the pressure is low, and below the wings, the air is slower and the pressure is high. The high pressure below the wing pushes more strongly than the low pressure from the above, so that it causes the wings and the airplane lift up. So, but this effect sometimes is harmful. For example, in a strong wind or in a hurricane, the roofs could be lifted off from a house by pressure difference. So again, because the roof usually is designed in this shape, in a triangle shape, so that the wind or the airflow above the roof becomes faster. And the high-speed wind results in low pressure, and such low pressure may cause the roof to be lifted up or lifted off from the house. So this is the Bernoulli effects. And try it yourself, blow up. So here is the experiment. We can do it together. Okay, let me see. Let me see if you can see my screen here. I'll try to do this experiment in the camera, through the camera. Now let's see. I'll pin this and make it bigger. So can you see me now? Now we can do experiments of the Bernoulli effects. So here I have a strip made of paper. So it's just a normal paper strip. So because of the gravity, so the strip in my hand, it's down. It's going down because of the gravity. So now if I blow the air in the direction, actually in the horizontal direction, which is going horizontal way, so what will happen to this paper strip? So let's try. If I blow it horizontally, can you see that? So what you can see here is the gravity makes the strip going down, but when there's airflow going in the horizontal way, the air moves fast in the horizontal direction, and this fast moving air makes the pressure surrounding this airflow to be low, because higher speed results in lower pressure. This is the Bernoulli's equation. So when this area has a lower pressure, then there will generate a pressure difference. So the pressure below this area is high and in this area is low. So the pressure will push the strip up so that you can see the strip is going up. So that's the experiment of Bernoulli effects. You can do it by yourself. Okay, now let me turn off the camera. Okay. That's the Bernoulli equation. Now let's try to that's the Bernoulli effect. Now let's try to derive the Bernoulli equation, which can describe the pressure, the velocity of the fluid quantitatively.
I had a science fair lab before, and you used uranium ore for experiment or something.
Do you have any questions? Because I hear someone is asking some questions. Is it for me? I couldn't hear clearly. So I guess it's not for me. It's some other questions. Okay, please mute your microphone during the class, unless you have a question. And feel free to interrupt me if you have a question. Okay, now let's continue the Bernoulli's equation. So here, let's take a look at some fluid in a tube. This is perhaps the most complicated tube or situation we can solve in this course. First of all, the fluid is in a tube, and the size of the tube is not uniform. It's wider at some part and narrower in some other parts. What's more, the tube is not even at a horizontal direction. The tube could rise at some part and it could go down at some other parts. Now, if some fluid is flowing through the tube, we can find some numerical relationship for pressure, height, and speed of this fluid by applying conservation of the energy, which is the kinetic energy change plus the potential energy change equals to the work. So this is from of conservation of energy. So because suppose the fluid is flowing through the tube, then there must be some forces pushing it. If there are some forces pushing it, then the forces are doing some work. Then the work could be transformed into two kind of energies. One is the kinetic energy, because for example, from here to there, the velocity of the fluid is getting faster, then the kinetic energy is changing. And from the beginning of the tube to the end of the tube, the height is different. Due to the height difference, then there should be some potential energy change. And more specifically, it's gravitational potential energy change. So this equation is true. As a fluid moves through a tube of varying widths, part of the segment of fluid will lose energy that the other part of fluid will gain. Now let's describe first the kinetic energy. Do you still remember the kinetic energy equation? The kinetic energy equals to 1/2 mv squared. M is the mass, v is the velocity. So M could be described by rho delta v, or rho v. So the kinetic energy could be described by 1/2 rho v, which is volume, and velocity squared. This is for kinetic energy 1 and kinetic energy 2. So suppose one liquid element is at the wider part, and we define the velocity is v1, and another water element or fluid element at the other end has a velocity of v2. Then we can use those two equations to describe their kinetic energies. The net change in kinetic energy could be K2 subtracted by K1, of course. And then now let's describe the potential energy. More specifically, it's gravitational potential energy, because now the height of the element, the fluid element, has been changed from low to high position. Then to describe potential energy or gravitational energy, it's easier. It's rho g v, or rho v g y, or it's mg y. So m is the mass, g is a gravitational constant, and y is the height. And m, the mass, could be described by rho delta v. So it's a rho delta v g y. This is for the fluid element 2, and this is for fluid element 1. So the change of the potential energy could be described by U2 subtracted by U1. And now let's see the work or the net work down to this part of fluid. So there should be two forces pushing this part of fluid. So one force is at the left end, the other one is at the right end. So the left end force is pushing it, let's say it's F1. And then on the other side, let's say it's F2. So the work done by F1 is work 1 equals to F delta X1. And the force could be described by the pressure times area, which is P1A1, then delta X1. So A1 is the cross area of this tube, and delta X1 is the length or displacement, which describes the force. Then A1 times delta X1 result in delta V, which is this part of the volume. The same thing here, F2. So F2 is pushing to the left. However, the fluid is moving to the right, which means the displacement of F2 is in the opposite way of the direction of F2. So the work should be negative. So the W2 or the work 2 is negative F2 delta X1. Again, F2 equals to P2A2, because F equals to, the force equals to pressure times area. Then we can reorganize it, because A2 times delta X2, it's the volume here. So it results in negative P2 delta V. So if we organize everything into the original equation, which is here delta K plus delta U equals W, and delta K could be written in this way. Delta U is written in this in this equation, and delta W could be written in W1 subtracted by W2. So finally, you will have the Bernoulli equation shown here. So if we rearrange it, this equation is Bernoulli's equation, which relates ideal fluid quantities at 2 points along a straight line. So here is the final version of the Bernoulli equation. It states that P, or the pressure, plus 1/2 rho V squared plus the rho G with height is a constant for ideal fluid in a straight line. Okay, so once we understand this equation, let's try to solve a real problem. First, let's take a look at this question. Water flows through the pipe here, which is shown in this figure. The water speed at the lower pipe is 5 meters per second. And then the pressure gauge reads 75 kilopascal. What's the loading? What's the reading of the pressure gauge on the upper pipe? And there are some, let's say, parameters given here. So the velocity at the beginning is a 5, and the diameter is 6 centimeters, and the pressure is 75 K. On the other side, first, the diameter of the tube is 4 centimeters, and then the height difference is 2 meters from the lower tube to the higher tube. Now let's calculate the pressure here. And of course, it's directly an example of Bernoulli equation. So we can use Bernoulli equation here to do the calculation. So from here, we know the P plus 1/2 rho V squared plus rho G Y is a constant. Now let's take a look at the two locations. At the beginning location, do we know the P? Yes. We know the pressure, which is 75 K. And then do we know rho V squared? Yes, we know rho is water, so it's 1,000 kilograms per cubic meter. So we know rho and V squared. Do we know V? It's 5 meters per second. And G is a constant. And Y, do we know Y? We don't know Y, but we can take it as a reference. Let's say Y, the height is 0 here. Then the height at this point should be 2. Okay, then we know everything in this equation for the left side. Now let's take a look at the other side, on the right side. On the right side, first of all, do we know P? No, we don't know. This is the question. We need to calculate P. And then, do we know rho? Yes, it's a density of water. Do we know V or velocity? No, we don't know velocity. And do we know G and Y? Yes, we know. G is a constant, which is 9.8, and Y is 6. Oh, sorry, it's 2 meters. So in the whole equation, we have only 2 things unknown, which is the pressure and the velocity here. So if we know the velocity here, then we can solve the equation to get the pressure here. So how to calculate the velocity? So we know the cross area, we know the velocity at the left side, and we know the cross area at the right side, then we can calculate the velocity by using the equation we have learned here, which is equation of continuity. Velocity times cross-section area is a constant. Okay, now the problem is solved. First, let's calculate the velocity at the higher point, and then we can use Bernoulli equation to calculate the pressure. Okay, first of all, we use the equation of continuity to calculate the velocity. V1A1 equals to V2V2. We know A1, we know A2, we know V1. The only thing we don't know is V2. Then we use this equation to do the calculation. Then you get the number of V2. Once you know V2, let's take it into the Bernoulli equation. So P2 equals to P1 plus this equation. It's from Bernoulli's equation. So everything is known on the right. You can calculate the P2 on the left. So finally, it's 4.6 kPa. So that's the way of solving problems using Bernoulli equation. Okay, so do you have any questions so far? If no questions, we will quickly go through the last topics, which is viscosity and Parsley's equation. Viscosity is a measure of fluid resistance to flow. A very viscous fluid flows slowly when poured. A real fluid or viscous fluid requires a pressure difference in order to flow at a constant speed. And the pressure difference needed to keep a fluid moving is proportional to the average velocity and the tube length, and inversely proportional to cross-section area A. And the equation to calculate the delta P or the pressure difference is 8 pi eta LVA. So L is the length of the tube, V is the average velocity of the fluid, A is the cross-section area, and eta is the coefficient of viscosity. So different types of material or fluid has different coefficients of viscosity. And here show some examples. For example, for air, the viscosity is really low. So this coefficient is low. And for honey, it has a very high viscosity coefficient. It's 600 at 15 degrees, and it's getting smaller when you heat the honey into 40 degrees. In an ideal fluid, all fluid particles move with the same speed. However, in real case, for viscous fluid, the fluid moves faster in the center in the tube, and the speed decreases as you move away from the center towards the wall. And if it's close to the wall, the velocity should be 0. So here is a velocity distribution for ideal fluid and viscous fluid. For ideal fluid, no matter where, you will see the speed of the fluid is the same. However, in a viscous fluid, the velocity is higher at the center and lower at the edge. And if it's on the edge, the fluid speed becomes 0. The average speed of viscous fluid could be calculated using this simple equation. So V average equals to R squared over 8 eta L delta P. Delta P is the pressure difference at the tube, or at the two ends of the tube. R, of course, is the radius of the tube. Eta is the viscous coefficient, and L is the length of the tube. And the volume flow rate of a viscous fluid could be calculated by Q equals to VA. And then A is pi R squared. So if you take pi R squared into this above equation, you will finally get this equation. The viscous flow rate equation is called the Parsley's equation, after the person who first performed this calculation. So in our examples, you will have some simple calculations, but by just using these equations. So all of the calculation are straightforward and easy. There are not too many difficulties in this calculation. Okay, so that's all for our fluid chapter. So do you have any questions, guys? If no questions, that's all for today. I'll stop the recording.